In this video, we will be discussing a data structure called tries. I will be discussing how trie works and what the pseudocode for trie looks like. Let's say I have a dictionary which consists of some set of words like tree, graph, data, etc. I will need to find whether a word given to us exists in this dictionary or not. One way could be that we can have a set where we store all of these strings and search one by one whether a word exists or not. However, the complexity for searching would be O of the size of set. Alternatively, we can also use a hash map or a hash table where these strings will act as the key for the hash table, and here searching would be O of 1. However, a more optimal way to store these strings would be using a trie. A trie is optimal because its complexity for searching a string is just O of L, where L is the length of the word we are searching for. And this is much faster than using a set and a little bit faster than using a hash table. Next, a hash table can be used to match exactly the occurrence of word in the dictionary, whether or not the word exactly occurs or not. However, a trie allows us to find words that have a character missing or a different character or that have some prefix in common. For example, given a word, we need to find its longest prefix which is present in the dictionary. Now for this, we cannot use a hash table. However, a trie would be sufficient. So now let's see what trie is. A trie is a tree data structure which is based on the prefixes of a set of strings. So here I have 8 strings starting from ABC, ABAC up till BB, and the trie which is built upon these strings is shown over here. A trie contains nodes and edges, and the strings are stored from top to bottom manner. A trie doesn't store the strings in a node. Instead, the string is formed by traversing the tree from top to bottom. Every unique path leads to a unique string in a trie. For example, say I choose the path from root to A, from A to B, from B to A, and from A to C. This path represents the string ABAC. So when we move from root to A, we add A here, and then from this current node, we move to the node B, so we append B, and from B, we go to the node A, so append A, and from A, we go to node C, so we append C. So basically, as you can see, the path in a trie is determining the string that is formed up till that node. And since this is a tree, there can be one and only one path from the root node to the desired node. So a node in a trie will have at most 26 children, meaning it will have at most 26 edges which are outgoing, and each edge represents a transition or an inclusion of an extra alphabet. Say this edge represents A, this edge represents B, this edge represents C, and this one D. So if we move from this node to this node, that means we are including the letter A. And for simplicity, instead of labeling the edges with the letters, we're just simply writing the node with this character A. So a node will have an array of the size of alphabet, which is 26, and each element in that will point towards a child node. And a transition using that edge will denote the letter being appended. So over here, this edge represents A, this edge represents B, and this edge represents C. A trie is based upon the prefixes of the string. Now what do I mean by that? Say I traverse from root node and end up at this node B. So the string I've processed so far is A, B. A, B. Now from this node, if I take any path to its child nodes, if I land up on any node whose path contains this node B, will also have the prefix AB. Meaning, if I come to this node A, the string representing this node will be ABCA, ABCA, and this will contain the prefix AB. Why? Because while traversing from root to this node A, we have come across this node B, and so the string formed by A must contain the string formed by B as its prefix. So in short, say from root I go to a node X, and somewhere in the path from root to X I encounter a node Y. Let the string formed at reaching X be S1, and let the string formed at reaching Y be S2. Then S2 needs to be the prefix of S1. Now every node we can have a Boolean variable which will decide whether a word ending at that node is present or not. For example, at this node C, we have a tick mark which states that the string formed from reaching C from root node is present in the dictionary. So the string A, B, C is present in the dictionary. Similarly, instead of a Boolean, we can also have a counter variable which counts the frequency of strings ending at that node, and also we can have some extra information regarding it stored in the node. So now let's see how we can build a trie given a set of strings. Let's start with the root node and process the first string ABC. We take the first character in the string, which is A, and there is no child node which transitions to A from root, so we will create a child node which transitions as A. Now for the next letter, which is B, we again create a new child node and transition to B. Similarly for C as well. Now we move on to the next string ABAC. So we come back to root and see the first letter, which is A. Now from root we have a child node which transitions to A, so we will come to A. Now from A we need to go to B, and we have a child node which transitions to B, so we will go to B. But from B we do not have a child node to transition to A, so we will create a new node which will be transitioned as A, and from here we will be creating for C as well. Now since our string ends here, we will mark the boolean and indicating that the word ABAC ends here. Similarly for the previous word ABC, it ended over here. Moving on to the next word, which is BCA. From root there is no child representing B, so we will create a child node for B, then we will create a child node for C, and then create a child node for A, and mark this node so that we know that a string ending at this node represents a string in a dictionary. Now for the next string ABCA, we will start from root. The first letter is A, so we will transition to the node A. From A, the next letter is B, so we will transition to B. From B, we will transition to C, and at C we need to transition at A, but there's no node for A, so we will create a new child node A and mark the boolean here. Now we will take our next string BBC. So from root we go to B, from B we need to go to B again, but there's no child node representing B, so we'll create a new child node which transitions to B, and from there we need to go to C, so we again create a child node for this and mark this boolean. Now for the next string BB, we start from root node, go towards B. Our next character is B again in the string, So from here we again transition to B, and since a string ends here, we will just mark the boolean over here, and we have essentially now built the trie for this set of 6 strings. Now, given a string, we need to check whether the string exists in the dictionary or not. So let's say a string is A, B, A, D. So we will start from root node. We take a first character, which is A, transition to the character A. The next character is B. We transition to B. The next character is A. We transition to A. And the last character is D. But there is no child node to transition for D. So we say that this string ABAD does not exist in this trie. Since we have stopped in this node, that means that the string which is represented at this node, which is ABA, ABA is the longest prefix of ABAD which is present in this dictionary. ABA is the longest prefix of this string which is present in the dictionary. Now let's say we need to search for the string BBC. So from root node we will go to B. Then from here we will transition to second letter, which is B, and from here we need to go to a last letter, which is C. So we come over here and we check here that a boolean is marked, which means that a word exists in this dictionary ending at this node. And so we can say that this word BBC is present in our dictionary. And say we need to search for word BC, right? So the first letter is B, so we transition to B, and then the second letter is C, so from B we go to C, and since this is the last letter that we have transitioned, we need to check whether the boolean here is true or false. So the boolean here is false. That means there is no word ending at this node. So this string BC does not exist in the dictionary. However, there are other words in the dictionary which has BC as its prefix. So in a sense, these searching operations, where we're searching whether a string exists or not, or we're searching for the greatest prefix, etc., is known as retrieval of a string in a dictionary, and hence the name trie. So it's retrieval, and trie is an infix of the word retrieval. Now we know what a trie is, how it works, and how we can build a trie. Let's look at the pseudocode for implementing trie and the time complexities of various operations in trie. The pseudocode for the structure of the node of the trie is given here. So the node will contain 26 pointers which points to the 26 different child transitioning to different alphabets. So if there is no child for a transition, we just have the pointer value as null. Next, we have a count variable which counts the number of words ending at this node, and a variable called prefixes which stores the number of words in the dictionary which has a prefix denoted by this node. Now let's look at the add operation for a trie, where we will be adding a word to our trie. So this is the pseudocode for adding operation. So this function will accept two arguments, the root of the tree and the word to be inserted. So we'll set the current node to be a root node, and we are processing the characters in the word from left to right. So for C character in word, we check whether from the current node, the child node which transitions to C is null or not. Say if it is null, it means that there is no child which transitions to this character C. So we create a new node and assign that node to the child. Next, we go to the child node. So we transition from current to current of child denoted by C. And whenever we transition to a child node, by one character, we increment the prefix value at that node by 1, because the string represented up to that node is the prefix of the string that we're trying to insert. So as we go from root node to the terminal node, all the nodes in the path will have their prefixes incremented by 1. And finally, when the loop is over, we will be in our final node, which represents a string. So that node must have its count variable incremented to denote that the word is present in the dictionary. Now let's look at the pseudocode for the search operation, wherein we will be searching for the string in the trie. The search function will accept the root as parameter and the word to be searched for as a parameter. So as usual, we set a current node to be root and process the string character by character. Now from the current node, if there is no transition to the character, then we simply return 0, stating that there are 0 occurrences of the string word. Otherwise, we transition to the child node representing character C. And finally, when we finish processing the string, we are at the node which represents a string. So we just return the count present at that node, which is current of count. And also searching for the number of words which has a specific prefix is very similar to this function search, wherein instead of returning the count value, we will be returning the prefix value, and our argument word will be the prefix which needs to be searched. Now let's look at the complexity for the trie data structure. The complexity for inserting a word in the trie is O of L, where L is the size of the string we inserted. This is because we visit L plus 1 nodes while inserting the string in the trie, including the root node, and hence the complexity is O of L. And for inserting n words into the trie, the complexity is O of NL. Here L will be the length of the longest string which is present in these n words. Similarly, the complexity for searching a word in the trie is again O of L, as at max we need to only visit L plus 1 nodes. So here it is, guys. We've discussed the basics of tries, how it works, and the pseudocode for some basic operations. I hope you have understood trie and the intuition behind it. If you have, please do not forget to like this video and hit the subscribe button. See you in my next video.